Hi, in this video we are going to talk about background for analysis of algorithms. Let us understand analysis with this example. You are given a number n, you need to write a function that returns sum of first n natural numbers. So if n is 3, then your output is 6, which is sum of 1, 2 and 3, right? First 3 natural numbers. Here the output is sum of first 5 natural numbers. Right? Please pause this video and try to write a function yourself in your favorite programming language, and then we are going to analyze all different types of solutions for this problem. Let us take a look at these 3 solutions written by 3 different programmers. Solution 1, it simply uses the formula for sum of first n natural numbers. So if you want to find sum of first 3 natural numbers, you will do 3 into 4 by 2, 12 by 2, you will get 6, right? And there is the second solution which simply runs a loop to sum numbers from 1 to n. So if you want to find the sum of 5 numbers, you will do 1 plus 2 plus 3 plus 4 plus 5. So you are running a loop from I equal to 1 to n. You will be adding I to the sum. First you will be adding 1 to the sum, then you will be adding 2, then 3, then 4, then 5. Let us take a look at this third solution. What this third solution does, it goes from I equal to 1 to n, and for every I, it increments sum by 1 I times, right? So we need one more loop inside it to increment the sum I times. So what it does, for I equal to 1, it increments the sum once, then increments the sum 2 times, then increments the sum 3 times. So this is what does for n equal to 3. So you get sum 1 plus 2 plus 3, right? For I equal to 1, this inner loop runs once time. For I equal to 2, this runs 2 times. For I equal to 3, this runs 3 times. So there are 3 different programmers who have written 3 different functions. Now how do you decide which one is better? There are many factors which come into the picture. This programmer might have implemented this in a different programming language. This programmer might have written it in a different programming language. They might be running their programs on different machines. And a programmer whose program is not good written might take less time if it is written in a programming language like C, where programs are really fast and probably running on a fast machine. So what mathematical tools you use, what theoretical analysis you do, so that you do not have to depend upon the machine, you do not have to depend upon the programming language. Not only this, you do not have to implement these 3 ideas and then decide which one is taking less time. The analysis which handles all these issues is called asymptotic analysis. And what we do in asymptotic analysis is measuring order of growth of a program or algorithm in terms of input size. Here I have written expressions for time taken by these 3 different functions. Let us understand how do we get these expressions. So the first function, it does constant work, right? How am I saying constant? If you take a look at this function and if you say I pass n equal to 10,000, what it will do? It will do 10,000 plus 1, 10,001, then multiply it by 10,000 and then divide by 2, right? And if you pass 100, then it will do 100 plus 1, multiplied by 100, then divide by 2. So the number of operations that you are doing is constant, not dependent upon the value of n. What all operations you are doing? 1 addition, 1 multiplication and 1 division, right? 3 operations. And these 3 operations are not dependent upon n. You are always going to do 3 operations, even if n is 10 lakh, right? So that is why I have written a constant C1 here, right? For the time taken by this function fun1. Let us now see fun2. Why do we get C2n plus C3? In fun2, we do some constant work, right? This is a constant work. This initialization of I is constant work. This is constant work. Constant means this work is always going to happen exactly once, whether you pass n equal to 10,000 or 1,000 or 10 lakh, right? But there is some work that depends upon the n. This will execute 10,000 times if n is 10,000, 1,000 times if n is 1,000. This I++ also depends upon the n. This condition check is also depend upon the n. So there is some work that happens n times. So if I say all this work that happens n times takes C2 time, and rest of the work that takes constant time. So we write the time of fun2 as C2n plus C3. So we have seen how do we get the expressions for fun1 and fun2. Let us now see fun3. What happens in fun3? We have this sum plus plus operation that is going to happen how many times? It's going to happen n into n plus 1 by 2 times, because sum is going to get that value at the end, right? Sum is initialized as 0. You can also see that this inner loop will run 1 times for I equal to 1. It will run 2 times for I equal to 2, 3 times for I equal to 3. So it's going to run 1 plus 2 plus 3 up to n, and which has the value as sum of first and natural numbers. So you have an expression that runs n into n plus 1 by 2. Right? Then you have more expressions inside it, right? So there's this constant work, right? So that is why I have written it as C4n square plus C5n plus C6. So C5n to cover this part, linear part, quadratic part, I have written C4n square, then I have written some constant to compute the remaining work, right? So that's how we get the expression for fun3. So we have got expressions for values of fun1 and fun2. Before we talk about this graph, there are few things I would like to clarify. When we do analysis of algorithms, we always talk about sizes of input which are larger than or equal to 0, because your input size can never be negative. So we talk about those mathematical functions which have input n greater than or equal to 0. Also, the time taken by your functions should also be greater than or equal to 0, because your algorithm or your program can never take negative time. So we always talk about this quadrant, this first quadrant of 2D coordinate system, where we have n greater than 0, greater than or equal to 0, and our funs, whether it is fun1 or fun2, they are always greater than or equal to 0, right? So that's what we do in time complexity analysis. We talk about this particular quadrant. Here I have drawn graphs for fun1 and fun2. Say fun1 is a function that you implemented and ran on your machine, and fun2 is implemented by your friend and he ran it on his machine. Now say you are running your fun1 probably on a slower machine and probably in a programming language that takes more time to run, right? And you get more time, your program takes more time compared to your friend, and your friend says that my algorithm is faster, right? Because he's running his program on a programming language which takes less time to run and on a fast machine. Now, how do you theoretically prove that your program is actually faster, your program, your function fun1 is actually better, and it's always going to perform better than the fun2 under certain conditions? To prove that, we do this theoretical analysis where we consider order of growth of both the functions, and we always talk about large values of n. So we are going to talk about some mathematical notations. We are going to call them asymptotic notations, and they are defined for n tends to infinite, right? Let's see this scenario. Fun1 and fun2. Fun1 written by you, fun2 written by your friend. Now you run it on a machine which is slow, so I've taken C1 slightly higher, say it's 10. It took 10 instructions on a machine to do that addition and then multiplication and then division. And say it takes 2n plus 5, right? So we get a graph like this on your friend's machine for the time taken. Now if you take a look at this graph, what happens here is after a certain value of n at this point, your friend's machine always starts taking more time. Now, how do we find this value after which your friend's program is always going to take more time? You can do this comparison. We want to find a value of n after which 2n plus 5 is going to be greater than 10, greater than equal to 10. Now what is the value of such n? N is going to be, if you do 10 minus 5, 5 you will get 5, and if you do 5 by 2 you will get 2.5. So if you're talking about integer values, you can say greater than equal to 3, right? So if a user passes n equal to 3, if your friend runs values n equal to 1 and 2, it's going to take less time in your friend's machine. But after you start passing values of n equal to 3, 4, 5, 6, 7, after any value of 3, your friend's program is going to take more time. Now imagine a situation that your friend brings a faster machine, right? And values of C2 and C3 reduce to 1 and 1 or 2 for your friend. And it gives you a slower machine. And value of C1 becomes 1000 for you. Maybe now you are running on your mobile and your friend is running even on a faster machine. Now this theoretical analysis now fails for small values of n. But if you talk about value of n when n tends to infinite, there is again going to be a value of n after which your program is going to take less time, even if you are running on mobile and your friend is running on a fast machine, maybe using a faster programming language as well. Let's see it in the graph. So what will happen now? I've used dot dots here because I wanted to show the value 1000 here, right? And this is your program's taken time. It's always going to take 1000 time. So in these graphs, I'm making this assumption that your CPU load is same and not other programs are running. We're making some assumptions here. And same is for your friend. So a friend's graph is going to look something like this now with this new modifications, right? Earlier it was growing faster. Now it grows slower because he has faster machine. Now if you compare these two, and if you try to find out a value after which your machine is going to take less time, you can find that value. N plus 1, you want it to be greater than 1000, your machine's time, you can find a value. Now for an input size n equal to 999, if you take this input size and the size after it, you are going to tell your friend, give some large value, maybe 1000 or 10,000, and then try to increase the value, and you will find a value where your program is going to take less time, right? Although this value is dependent upon the programming language and machines, but this is guaranteed that there is going to be a value. Why is it guaranteed? How is it mathematically true? We'll talk about that in the next video. In this example, we found a value 999, and this is where this value is in the graph. After this, you can see that this linearly growing graph has always more values, right? It's always going to be more because it grows like this and this grows like this. Same thing happens when you compare Fun3 with Fun2 and Fun1. Fun3 is a quadratic graph, right? So Fun3 is going to grow like this, right? It's a quadratic graph. So it's going to grow much faster than Fun1 and Fun2, right? In terms of input size. The constants, they would matter, but when n tends to infinite, they can be ignored. And we are going to do this mathematical analysis in the next video.